In this video I will try to improve the phase noise of this oscillator. In the previous video, nerds100, I established the sensitivity towards changes in the supply voltage as 0.2 Hz per volt and also 2.3 degrees shift of the phase angle per volt, means 0.1 Hz per degree of phase shift. Here is the schematic diagram. First is one amplifier stage with a crystal filter, which is not in use now and hasn't been for a long time, because first I want to have good performance while using only one crystal. So input is here, and then there are 6 parallel junction FETs, J310. And then the next stage here is 6 groups of 2 junction FETs. And then finally 6 groups of 2 junction FETs again. And then there is the output. And feedback output comes from this stage. Now, my idea about the problem is that all these FETs suffer from flicker noise, and the flicker noise gives rise to a varying supply voltage, because current is supplied through a big resistor, and then there is a big capacitor parallel to the unit at 16 volts. So what I will start to do now is to replace these transistors by bipolars that should have smaller flicker noise, particularly since I will use fairly large emitter resistors to get current feedback to keep the current constant through the transistors. I'm using lean rod to measure phase noise at the close range. As you can see on this screen, it has been running for 15.5 hours, so statistics is very good. Now I have enabled network, so the raw data is sent and is available on the network. So I have a second screen here with different sets of parameters, so I can see the noise floor at 10 kHz offset at 181.5 roughly. And here you can see sensitivity bends off. It is easier to see here because this is horizontal and then it bends. And that is because I did not calibrate the sound card. So I will do that before continuing. And then I have a third instance of Linrad running. And here I'm looking at Allen deviation or Hadamard deviation. This is the Hadamard. Now you can see something happened here. That is that the PLL stopped working. I got outside the capture range, or what it's called, lock range. So channel 2 is now running some 4 millihertz away from channel 1. This jump makes a big difference in the red dots here, which is the Hadamard variation computed from the channel 2 oscillator and the oscillator under test. The green signal seems to have been okay all the time, so that gives a better result. And then the correlation between red and green is a little bit below the green, except here at about 100 seconds where the correlation happens to be negative. That's because statistics is very poor at 100 seconds. Not so many correlated averages. So if I would wait for a very long time, this would probably go up somewhere here. Now the fact that the phase locking has failed, I can see that here, down here. I don't think the camera can do this. With much more white on the screen, maybe you can see that the red curve is a little to the left as compared to the green. It can be seen here. So the difference is really very small. You have the scale here, 0.1 hertz, 0.1 hertz for one division. And as it turns out, the oscillator has locked now. And I can see that the locking voltage is very low. So the channel 2 is a little bit out of tune. The fact that the oscillators were unlocked for a short time does not affect the phase noise measurement, because the time shift is extremely small, or zero. It's just a phase shift for a while. So I can use this information to see what is the performance of the oscillator today. It's easiest to read the values in the linear frequency scale. So I can see at 0.2 Hertz it is 94.0 minus 94.0 dBc per Hertz. I can read frequencies up to almost 10 Hertz. That's here. This starts to be perhaps a little uncertain because I have a phenomenon here. I don't quite understand how it happens, but I can see here the frequency is 9,999 kilohertz, 0.920738 hertz. And the nominal frequency is 10 megahertz. That is the label I have put on my reference oscillators. So the audio frequency is 10 megahertz minus this comes out as 29.262. And if I divide that by 2, I get 14.6. 14.6, that's here. So this structure is half the frequency of the zero frequency, as well as the distance to the second harmonic. And it's quite clear the signal I have here is the second harmonic, and the noise around it is the zero frequency noise. I have another false response here at about 21 Hertz. And at the moment I don't know the reason for it. Here I can see that the noise floor at 10 kilohertz down here is minus 180.7. The differences with the previous measurement in nerds99 are very small, about 1 decibel here, and here, and here 1.5. The new data points are the rectangles, the squares. They fit better to the line I draw previous time. So some statistical uncertainty. It is the same result, essentially. The first thing I want to look at now is to see how the phase noise depends on the power level when I change the coupling capacitor to the crystal. In order to do that, I set one of the generators to 10 dBm at 10 MHz. And then I run the signal through a bandpass filter to remove the overtones, and then from the filter into the spectrum analyzer. And here I can look at the level, and it says 9.4, 39 or 4. I have decreased the sweep bandwidth and the video bandwidth, so I get a stable reading now at 9.46 dBm. Just a little higher because the find the peak maximum is more accurate now. I have moved the cable from the spectrum analyzer to the oscilloscope, so it's the same cables and the same 10 MHz filter. So I know this is an almost perfect sine wave, and I measure the level as 1.81 volts. And I move the connector to the other input, and the result is exactly the same. And both inputs are 50 ohms now. And then I move the cables to another oscilloscope, and then I see 1.90. Channel 2 on the second oscilloscope gives me 1.86. I found that the spectrum analyzer tells me the level is 9.46 dBm, while the oscilloscopes gave slightly different results, but in decibels this is very small differences. The average of these four readings is 1.845. That gives me 8.51 milliwatts, and that is 9.25 dBm. A difference from what the spectrum analyzer gave me, 0.2 decibels. And that is a small enough difference, so I don't have to care about it anymore. So I will use the readings directly from the spectrum analyzer. Actually, when I take the same signal, moving it from the oscilloscope to the cable that I usually use to route signals up to the spectrum analyzer, here it comes. It is several meters long. So now I read 9.2, and the proper value would be 9.25, but the uncertainty is larger than the discrepancy. So I have a well-calibrated reading here now. And I move the cable to the oscillator. And then I see that the level is 16.89 or maybe 16.90. It moves a little up and down. Peak search marker. Well, 16.89. And of course the last decimal isn't important. The level 16.89 gives me an AD margin to the saturation point in channel 4 of 1.08 decibels. And that is with the channel 2 attenuator. This one set to 21 decibels. I have tested all combinations of 10 dB stepping and 1 dB stepping on that attenuator. So 0, 1, 2 and up to 10 for the fine, and then 20 dB, 10 dB, 0 dB, and then 0 dB once more. And the power level is different each time, differs by about 10 dB, plus 16.89, plus 6.88, minus 3.12 and minus 13.15 dBm. And the result of all of this is that here is the attenuation for the different settings of the fine knob. They all are within a fraction of a tenth of a dB, except for the 10 dB, which differs by 0.12 decibels from the average of the other ones. And that is an error of 0.1 dB, nothing that they will worry about. And for the cause setting, then I look at correct for the different power levels. They are 0, that I call this 6.89 dBm for 0. Then I have minus 10.01, minus 20.01, and minus 30.04. Because at the level setting on my signal generator is in 0.1 dB steps. And I didn't want to spend more time on this, because the result of this is that the 10 dB and the 20 dB cause steps are accurate within better, significantly better than 0.1 dB. So I can just use this attenuator as a precision instrument that facilitates what I'm going to do. This is the formula I have found. It is accurate for all settings except when the 10 dB position of the fine stepping knob is used. Then there is an error of 0.1 dB. Not much to worry about, but the other settings are better, and the 10 dB setting is never needed because it's better to step up on the coarse scale. Unless, of course, I would need the full attenuation at 30 decibels. But that's a quite high power that I'm not likely to get from oscillators. I have adjusted the coupling capacitor to the crystal to get an output power 2 decibels higher than I had before. That means 18.8 dBm. Already after 10 minutes I can see that more power was a bad idea. At 0.2 Hz I had about 95 before. That's here. And I have lost probably 6 decibels at 0.2 Hz. On the other hand, of course, at wide separations it is very likely different. That can not be decided as quickly, but if I look at minus 180, you can see clearly that the noise is probably 2 decibels lower, as it should be, with more power. But I want a good performance at very close range, and better than 180 is good enough. The Allen deviation is not so good. That's because I had the box open to tune it, and therefore it is drifting a little bit for a while. So I would have to wait for it to stabilize until I can get Allen deviation. Hadamard is less sensitive to this type of problem, so it looks a little bit better. And it is the green trace up to about 10 seconds that can be trusted. Statistics is not good up here. I leave it running for a while because I want more accuracy on the result at 0.2 Hz. After a little more than an hour, it is very clear that this here is much more noisy than what I see here. I will read a couple of values from the graphs. At 10 kHz, the noise floor seems to be about here. That's minus 182. So improvement is a little less than 2 decibels. But on the other hand, the imaginary part is pretty close, so this can go down if I would wait long enough, which I'm not really interested in. When I use linear scale and compress a bit, then I can see minus 182 here. And it may go down a little bit more, but the effect of the sound cards start to be a problem. So it looks like there is an error of about 2 decibels there. So that's 2 decibels here, means I get that minus 182. At a separation of 1 hertz, the difference is about 10 decibels because of the 2 decibels higher power. It is more of a straight line now, so at 0.2 hertz the difference is a bit smaller, and it seems that the lines would cross, although I don't know because this could start to bend. But I think there are different mechanisms. This bending, which I associate with capacitance variations in the FETs, is hidden below the noise that comes from excessive power. And how that happens, I don't know. Hope I will find out later on. The power level is now 14.9 dBm, 2 dB below the original setting. And this is not quite as good. I see now minus 92 dBc per hertz at 0.2 hertz. I will make a linear scale and read out some points. I have been busy doing other things, so this measurement time is very long, 24 hours. So I can read all the way up to 10 hertz now. And then comes these phenomena. I don't know exactly what they are, but 10 hertz minus 152 about. At 10 kilohertz it is minus 179. Noise versus output power. Going from 16.9 to 18.9 causes loss of performance from 6 up to 11 decibels at various frequency offsets. I didn't take all the points because I don't have any interest in running at this power level. At 14.9 dBm, the loss is 1.6 dB at 0.2 hertz, and then it is smaller at 0.3, and in this region from 0.4 up to 1 hertz there is a small improvement, and then at 1.5 hertz there is a significant problem. I don't know why, but this deviates in a funny way. And then the values are small, probably not significant here, because statistics is not so good down here. Anyway, this looks like a hockey stick, famous from the climate debate. Very flat and then suddenly up with increasing power. I have run the calibration procedures for Leanrod to flatten the frequency response when I go up to 10 kilohertz or above. Now, that didn't work well because the calibration algorithm introduces some spurs. Not very strong, but here I am looking for weak phenomena together with a very strong signal. So spurs become far too visible. But I have done something else. I found the reason why it was not possible to have higher than 48 kilohertz on the network. And the reason was that the receiving copy of Leanrod would send messages back and using the same thread as was used for receive. And that blocked receive for a couple of milliseconds too much. So there is no reason to send any information back when doing sideband noise measurements. So now I'm running at 96 kilohertz, and then I don't have to do any calibration because the sound card is flat enough. But I have done some other experiment before I start to modify the oscillator. First, here is the same measurement as you have seen before. It shows 93 dBc per hertz. And then I have here the measurement that goes up to nearly 20 kilohertz, and it is flat now, as you can see. And whether it starts to go up here or not is hard to judge, because the imaginary part comes up and is too close. This is after 3 hours and 20 minutes. Then I have the Allen variation. Here you can see the yellow curve, which is the difference between channel 1 and channel 2 oscillators. And it has a peak amplitude of about 1 millihertz. And if I click on the star here, you can see the green and the red traces. Green is channel 1 and red is channel 2. And the pace locking time constant is very long. As you can see, the red and the green, they meet at something like, is it 2, 3, 4, 5, 6, 600 seconds, then they are correlated again because of the PLL. So it means up to, say, 50 seconds, they are independent. So I can trust the yellow trace, which is the correlated part, which is well below one or the other. And one should be able to see that by inspecting these curves, but it's a bit hard to draw any conclusions. Then I have added a fourth measurement here, where I go all the way down to 0.04 hertz from the carrier. Something goes wrong. You see here there is a red line. There is a very strong glitch in the data stream. Now Linrad has a feature. You can see here are red numbers. It says skip FFT 3, 57 decibels. That's the amplitude of this spike. Normally it should be minus 10 or something. So it is red and it doesn't collect statistics from this transform. The interesting thing is to compare the result close to the carrier from this measurement with the other one, because the other measurement, it showed only 93, but here I can see about 97. And that seems to indicate that the reason for the curvature of the result at very close range to the carrier has to do with the measurement rather than the oscillator. So I will plot these data to compare them and then decide what parameters to use for measurements when doing modifications to the oscillator. The system monitor shows that I am using about 80% on some CPU cores, but most of them are below 20%. The memory, I'm using 1.2. Memory, I'm using 40% of the memory, 26 gigabyte. I have 67.5 to use. And, well, so I'm not overloading the machine. This is the glitches I see. Here is a software issue of some kind that I don't know what it is, but maybe I can find out. The linear frequency scale is best to use when reading information on the screen. Here I can see 0.2 Hertz is at minus 97. But if I go to the previous kind of setting, which is much faster, at 0.2 Hertz I read minus 94. So that is a 3 decibel error in this measurement. And that's probably because I'm going too close to the carrier. So there is some contribution of the carrier itself in the Fourier transform. I have misjudged how close I can go, it seems. Now a transient is on the way in. Check this spectrum now. And here is the next transform, and you can see it is a flat line. And above 100 dB, 105 maybe. Linrad switches off while this is being processed. There is no corresponding glitch in the master which is sending to the network. You can see this is perfectly clean all the time, except here when I suddenly made some careless movement. When I compare the slow measurement that goes down to 0.05 Hertz from the carrier to the normal one I'm using, which is much faster but goes only to 0.2 Hertz, then I find that at 0.2 Hertz the difference is 3.2 decibels. At 0.3 Hertz it's 0.4, and at higher offsets it is so small, so it is well within the statistical uncertainty of the measurements. When I plot the numbers, this is what I see. So from here all the way up here, the points coincide. This one is off the extrapolated line. That was 5 Hertz, and I think there is a spur there that contributes. It is a wide spur, and this 5 Hertz is on the edge of it. But at 0.05 Hertz, these red dots start to bend. I have plotted the f2 minus 3 and f2 minus 4 slopes, and we can see that the curve goes from minus 3 to minus 4 somewhere. Well, it is a soft transition. Anyway, I can expect the lowest, the closest to the carrier of the slow measurement, has a part of the same problem as I had here. So this is, I am too generous in allowing measurements too close to the carrier. So I should change by a factor of 1.5 to bring down the error from 3 decibels to half a decibel. The average phase noise, which is now minus 126.11, is computed for all the frequency bins that are on the frequencies where the scale here is green. It's from 0.2 up to nearly 3 Hertz. I have changed Linrad to make the first point bin number 12 in the FFT. Previously it was bin number 8. And I noted this 3 dB error. The first green point is also the first point when I show the logarithmic scale. The average value is printed on the standard error. I have run now for 7 hours and 40 minutes, and it is 1,598 averages. And you can see the value is constant within 1/100th of a decibel. Now I can look back in time, and we can see it was here 07, 08. And I cannot look longer than back to point number 600. But you can see it is 25.99, 26.
So it changes slowly over time. I don't know whether it is really the phase noise that changes or whether this is just a statistical variation. I will restart to look how many averages are needed to get a stable number. That is Alt Z. And I have to have linear in focus to do that. Now I am starting. The first point is minus 125.92, then 0.77. And I think I will have to wait for 10 minutes or something like that. This is 10 minutes. I have 35 averages, and at this point the average is minus 126.4. That is 0.3 decibels off from the long time average I had. After half an hour, I see minus 126.35, and it has been around from 35 up to 48 and then down to 30. So it is oscillating a little bit, and it's about 0.3 dB better than what I saw over a long time, overnight. Maybe the temperature had changed a little, because I think this is not statistical fluctuations, this is variations in the sideband noise. Well, that's a hypothesis. I'm not really sure about it. I have changed the supply voltage from 16 volts to 15 volts now. That has caused a frequency jump. The frequency was 974,679. And now when I moved the signal by putting the cursor on top of it here and click, then it changes to 974,609.37. The difference is about 30 millihertz, and I have had the Alan deviation graph running on the same signal, and here the frequency scale tells me it is minus 182 millihertz or something like that. Obviously, I have made an error in the frequency scale. I will have to correct someday. I have magnified the frequency scale, and you can see now there is a strong drift as the temperature is changing. So I will have to wait for it to stabilize. Or maybe I don't have to do that. I can look at the noise that I have seen so far. It is minus 126.6 or so, or 7. And it's not a significant change. Well, the temperature looks stable now, after about 700 seconds, a little more than 10 minutes. I will reset again the average, Alt Z, and see if there is a difference or not. The noise at 10 kilohertz offset is minus 178. I haven't reset here, so this is collected for the latest 8.5 hours. So this is the result at 16 volts. I will clear it and see if there is a difference now. Well, after 25 minutes and a half, I have the same result, minus 126.44. So it seems a small temperature change. The power is a little bit lower because of the lower voltage. That hasn't changed the sideband noise. And the wideband noise at 10 kilohertz has not changed either, but here the accuracy is not so good. I have tried some different configurations for the amplitude limiter. The original one, 120 ohms, and one pair of diodes. It's Schottky diodes, 1N6263. Then I made 2 series connected diodes and lost nearly 1 decibel on the average noise. So I tried to go to half the resistance, and that improved. I got nearly the same result as here. And then the last step, I kept 60 ohms and just a single pair of diodes, and this is better. So the conclusion of this is more power in the diodes is better, more current. To get more power into the diodes, I have increased this resistor from 560 to 820 ohms. This has increased the output power by about 3 decibels. So the current through this should have increased by a factor 1.4 about. The average noise is about minus 127 now. But what's interesting is that 0.2 Hertz, which I have here, seems to be below minus 100. I will wait for quite some time to get good readings and to compare the shape of the curve with what I had before. After 16 hours and 40 minutes, I see minus 126.62, and that's the same over all of the measurements. But of course they change very slowly because it is now the average of 3,429 averages. And adding one more cannot change much, even if it is rather different. Anyway, the interesting thing is that the curve looks better at 0.2 Hertz than it was before. I look at the linear scale, and here at 0.2 Hertz I can read minus 102. And if I look at the line, how it has a dip here, I can guess that maybe it would be more appropriate to call this minus 101. But it is significantly better than the previous result. The settings that give me information down to 0.03 Hertz approximately doesn't give good enough statistics yet. It has been running for only 12 hours and 20 minutes, but I can guess, if I look here, that the result at 0.1 Hertz will be something like 91 or maybe 90, minus 90 dBc per Hertz. And 0.05 is very unprecise because the channel 2 oscillator is quite noisy at this very low offset from the carrier. But at 0.2 Hertz the result is reliable, and it is 100.5. And here both my reference oscillators are 4 decibels above the noise of the test object, which means that the oscillator I'm measuring is better than both oscillators at this offset. If it was equal, it would differ by 3 decibels from the yellow trace to the other two. When I look at the linear scale up to 280 Hertz, I see something very odd. The phase noise is constant over the entire range, and it is at minus 143 point some small decimal. This means I have had a glitch that is silicon into the system. It is a frequency jump of the oscillator I'm making measurements on that has somehow gotten into the system. So I would have to reset, but this thing is linear all the way down to 0 offset, I can assume. So it means that it doesn't affect the readings I get down to something like minus 135 or so. And that happens at 2 Hertz offset. So I can trust numbers up to 2 Hertz offset from this measurement. At the same time, I have been running at high speed, and here you can see that this transient has not been allowed to enter the measurement. So it shows that the noise floor is at minus 180 dBc per Hertz, and I can see it should be at the 200 Hertz or so, where I saw minus 140 something. But here I can read minus 174 or something like that, between all the overtones of the audio frequency. And this measurement, I have to change scales, and that is a slow procedure. Here I can see the noise spectrum up to about 5 Hertz offset. And I don't know the reason for this ugly structure, except that the distance from these values to the imaginary part is about 0. Here it's even negative, and these readings here are far below the noise of channel 2, so they need a lot of statistics to become reliable. This has been running for 12 hours and 40 minutes. And I can see here, at about 2 o'clock in the morning, UTC, the frequency made a jump. And I think that is the explanation to the peculiar flat noise I saw in the first measurement. And for this measurement, the Linrad stop collecting data when there is a big transient seems to have worked to not include the data where this jump was in the buffers. When I compare the results I have now with the previous measurement, before I tried to optimize this time, I see that there is no difference above 0.7 Hertz. The two types of measurements I do simultaneously here and here, and they don't differ. And that's correct all the way up to 2 Hertz. At 3 Hertz, this measurement is disturbed by this frequency jump, so I have to look here, and then they are equal. But at 5 Hertz, there is a small difference, 1.5 decibel. When I look at the curves I drawn on paper, it becomes more clear. All the points fall now on a straight line. Here these are the blue points, and here they are the same, and then at this point I had a spur. This time I don't have. And this line is a slope that is very close to F frequency to power minus 3. So this is satisfying and a little bit surprising now. I saw an improvement on the average noise from 0.2 to 3 Hertz. And these points have not changed, so the change has been only very close to the carrier. I added these white foam strips on top of the original material I had here. Well, I cannot remove them easily, it seems.
that is not possible. The adhesive of this dust sealing strip was really difficult, but I found this petroleum product could dissolve it quite well, so I could clean the surface and restore the original sealing I had for Infrasound. Now that I know better what to look for, I do new measurements to see whether some degradation has happened because I removed that sealing strip. Now there is only the original one in place. So I will look at the average phase noise over the green region from 0.2 to about 3 Hz. And I also look at the noise from 0.2 Hz up to 0.7 Hz. It is minus 109 right now, and the previous one was 126.3. But I will wait for a while to have a more accurate result. I also look at this screen, which runs with a narrower bandwidth. Here I get the average from 0.05 up to 0.27 Hertz approximately. At the moment it is minus 89.4, but I will wait for a while. I have negative values here, and that's not really so good. They are just excluded, the negative values. And then I have this screen, which gives me the noise at 10 kHz. It's about minus 181, but I need better statistics. And finally, the Hadamard variation, which has at the moment 1.8 times 10 to minus 13 at 1 second, and 1.36 to times 10 to minus 12 at 10 seconds. The noise I see in the waterfall here, it doesn't look quite as white noise because there are as noise bursts, and here it is quiet for a while. But it's a very small structure, but this could be infrasound. The reading I have here at 0.2 Hz is minus 94, and that's not particularly good. Now I have fairly high power at the moment, so I am going to do this with different power levels, a couple of them. I have made measurements now at different power levels with only the original sealing strips. And now I have put back these extra sealing strips and will repeat the measurements. Here is what I see with that extra sealing strip to keep infrasound out. And I have saved the previous, which you can see here. Here you have more noise. It's clearly visible. And of course in the phase noise spectrum, here is the old and here is the new. And it differs by something like 4 decibels. So obviously the old sealing tape or strip or what you call it was not adequate enough to keep pressure variations out of the box. Here is the measurement on my desktop number 4, where I am looking at the slightly wider frequency range. And we can see here at 0.2 Hz about, here is the new measurement, and here is the old. And there is a difference of 4 decibels or something like that in this range. But if I look here at 2 Hz offset, the difference is much smaller. And if you see here,
The difference is mostly the statistical uncertainty. It is obvious I have had the problem with infrasound, and now that I know I have a f2-3 dependence over a fairly wide range, I can do measurements much faster by averaging over a wider range and also skipping the very closest because they require slow processing. When I measured with the original ceiling strip only at 18.5, 16.5 and 14.5 dBm, I was running for a long time, 9 hours on desktop number 1. But the network had crashed, so I restarted and ran only for 2 hours on the other screens. So if I look at the result as a function of power, I find the same result for what I call average 8. That is from 0.05 to 0.27 Hertz. That's the region where we have infrasound problems. Also in desktop 4, which was running only 2 hours, the difference is fairly small, 109.9 up to 110.1 for the average 12, which is from 0.2 to 0.74 Hertz. And the other here, average 3, which is from 0.2 up to 3 Hertz, differs very little. So it seems performance is now independent of the power after I changed the power into the amplitude limiter. And then the difference from this line to this line is with and without that extra ceiling strip, the white foam plastic. And that makes a big difference in some of the columns. Most here, the average is close to the average 8, which is from 0.05 to 0.27. And also here, which is the noise at 0.1 Hertz, and also the noise at 0.2 Hertz. Nearly 4 decibels, and here 4 decibels. And on the average 4 decibels. But if I look at 10 kilohertz, there is no difference at all. And the phase noise differs by 2 decibels in the measurement on desktop number 4. I don't know exactly why, but I think maybe the infrasound varies a little with time. And here, average 12, which is 0.2 to 0.74 Hertz, the difference is 0.9 decibels only. The conclusion from all of this is I do not have to make these many measurements, and I don't have to measure all the way down to 0.2 Hertz. I can start at, let's say, 0.5 Hertz, which will make the measurement faster. Because when I look at the curves, I now know that the deviation, that the curve, the red measurements I made before, start to go up with a steeper slope below 0.3 or 0.4 Hertz. That is because of the infrasound. Without the infrasound, I have a straight line. And I want to know how this straight line moves up and down when I change things. So I can skip the last couple of points and then do measurements all down to maybe 4 Hertz or something. I will look which region has the best signal to noise ratio, and do measurements within that region. And here I can see what is the best region. At 4 Hz, sometimes at 5 Hz, this structure that I don't know what is causing it is degrading the measurement. So I think I should not go higher than about 3.5 Hz. And then at the low side, starting at 0.2 Hz, means I don't miss so many data points. So from 0.2 up to 3.5 will be what I think is optimum. For an accurate result, I have to run until the curve, the yellow trace, is within plus minus 2 decibels or something close to that. This peak was negative a few samples ago, but when it switched from not being counted to be included, I got data points here that are very far from the proper value, and that means that the average will make jumps of a couple of tenths of a decibel, going from 0.50 down all the way, and then 0.8, and now it goes down. So I have to wait a little bit longer than this. This is 11 minutes. There is a spur here about 1 Hz from the carrier. There is 1 Hz from here to here. And I can see it here. It's only in channel 1. Or at least it is much stronger in channel 1. Whether it is also in channel 2 or not is too early to say. If I wait long enough, I can see that on the correlated curve, whether there is something that is also present in channel 2. Anyway, it is weak enough to not affect the average noise over this entire range. Now, most of the data points are within plus minus 2 decibels. 2.5 here, and also here, but very few. And this is 24 minutes with 82 averages. I will run this for a much longer time to see whether the conclusion I have minus 130.5, 47 the last point, but that is 0.5. The largest deviation from the value I noted, 130.48 here, is 130.36 downwards. And 0.50, 130.50 at 0.97. Then it converges to 130 point, I would say 43 or something like that. I have set different values on the attenuator from 11 up to 27. And then I have adjusted the tuning capacitor for an AD margin of usually 1.5. At this point I had a spur, so I had to go to 1.6 instead. This means I have set different power levels. And then there will be different frequencies. And at this point I increased the coupling capacitor, so I get 2 values with different frequencies at 14.5 dBm. And they don't differ much. And that is what I have expected, that the power is important but not the frequency.
Anyway, the last data point here, that is a point where the unit is saturated. So reducing the tuning capacitor did not increase the power. So this is a measurement very close to the saturation point. And performance has degraded significantly. And here 18 dBm seems to be a reasonable level where to run the oscillator. So I went to it and found 130.2. That is close to the best values I have seen. There is of course a statistical uncertainty, particularly the very first point, only 84 averages, so it is a little bit high. When I plot the data points from 5 to 22 dBm, I see a curve that looks quite reasonable. Very low power levels, there is a loss of performance, then it seems to be fairly flat here, and then it drops very fast when it approaches saturation.
I have set very slow processing parameters. In 2 hours 40 minutes I have collected only 12 average spectra. The reason is that I now suspect that the excess phase noise of channel 2, it's at about minus 23 at 0.01 Hz, while channel 1 is at minus 35. So it's more than 10 decibels excess noise here. And there is a corner frequency at about 0.15 Hz. Below that they follow each other, the two channels.
This is the channel 2 oscillator. It has this kind of foam sealing strip. I will add one more layer of it to have it more compressed, which should make it tighter. Like this. Now the yellow and the white will be very much compressed when I put the lid on. This oscillator has now degraded. The phase noise is significantly higher than it was before, and I have done nothing, no change to it, it has just been running.
The average noise, which was before minus 130, is now minus 126.56. It has degraded by 0.1 dB now, because when I started this recording I made some vibrations on the table while placing the camera on its, I don't know what it's called, the unit on which I have fastened it on the table. I made some vibrations. But the curve has not changed significantly, so I will read the numerical values at some frequencies. At 1 Hz, minus 123, for example. At 0.2 Hz, here, minus 94.0. As it happens, I get no decimals this time. 0.3 Hz, 102.0. 0.4 Hz, 108.0. These are the data points I see now. And I should have expected the blue points here. And the difference at 0.2 Hz is 8 decibels. It's a big loss of performance. I don't know the reason, but it could be that the box is no longer well isolated from infrasound. The foam list may have aged somehow, so it is no longer keeping infrasound out. Or it could be something else that has happened. The foam strips have been pretty well compressed. Maybe they are not really airtight anymore. So I will add a second layer of foam strips on top of these. A second layer of plastic foam sealing strip did not make a significant difference. I have now 126.63. I had 126.50. And this is only 189 averages, so this could well go down to 0.50. It is 0.70 up here, and it is, well, going up and down a little. Normal statistical fluctuations. So I don't think this is infrasound. The only other thing I have changed recently is the power into the clipping diodes. So I will replace those diodes with twice as many diodes, with 2 Schottky diodes in each direction in the amplitude limiter. The AD margin has changed from 2 decibels to 4.75 decibels. Means that the power is reduced from 18 to 15.25 dBm. But the average noise, the average sideband noise, is still 126.5. So this was not the important thing. I have reduced the tuning capacitor to restore 2 decibels of AD margin, which means I now have 18 dBm output from the oscillator. And this has not made any difference on the average phase noise. It is still significantly below what it was a couple of days ago. And I haven't changed anything as far as I know. Only the 2 latest changes, meaning more isolation against infrasound, made no difference, and 2 diodes in parallel in each direction for the amplitude limiter. I have set very slow parameters so I can go very close to the carrier. When I look here, I have a straight line over some fairly large distance, but at 0.2 Hertz it starts to deviate, and here at 0.01 Hertz the difference is 15 decibels or even more. And I can see here that channel 2 is much worse than channel 1, and that is below 0.1 Hertz here, and it runs steeper. And I can see also the yellow trace, the correlated, looks odd. Of course, statistics becomes less good at lower frequencies. There are fewer bins here, but this looks like a structure of some kind. I don't understand. I don't know what is going on. And of course, statistics is degraded by the distance up to the channel 2 signal. The transform size here is 20, and here it is 19. And the size of the transform, FFT3 size, is 500,000. And of course, for this transform, then it's twice as big, about 1 million. And the sampling rate 750 Hertz. This means that one transform spans 1,398 seconds. And that is, if I divide by 60, 23 minutes. So it is really slow. Now, the transforms overlap to some extent. So in the period of 14.5 hours, I have collected 164 transforms. And this variation here is very large. Even though it is 10 decibels up to the red trace. I don't know what to say about this. I just can say that I don't like it. I have been running fast transforms in another desktop at the same time on the same data. And here I see that the 10 kilohertz is here. 181.5 and 182 at 20 kilohertz. So that's okay. And the standard parameters that gave me some time ago, minus 130 for the average from 0.2 up to 2.9 or maybe 3 hertz. It is now giving minus 126 as I have had now for some time. The current oscillator, which has degraded significantly for unknown reasons, it was never very good at very close range. But as I can see here, the channel 2 oscillator is significantly worse than channel 1, and also of course worse than the oscillator under test. Here I have connected a rubidium stabilized oscillator instead of my crystal oscillator, and I can compare them. You can see here there is a big difference at 0.05 Hertz, but the slope is very different. It goes like this, and the other one goes like that, or like, and even steeper. Now this is better seen in the Allen deviation graph. Here you can see Allen deviation. It is at, for example, 0.3 seconds, something like 3 times 10 to minus 11, while with the FET oscillator it was something below 10 to minus 13. But it would go up here, and the rubidium oscillator, the real performance is probably going downwards quite a bit. I don't know how long, because that's not what I can see with this setup. But what I can see is this graph down here of frequency versus time. The green trace, that's the oscillator in channel 1, while the red trace is channel 2. The yellow trace shows the difference between the two oscillators. But we can see that the green trace is fairly close to 0 frequency offset, while the red goes easily plus minus 0.8 or so. Here it is minus 1.2, and here is it plus 1.2. And the difference is up to nearly 1 millihertz. The optimum solution for a test system like what I am using now would be to use the rubidium oscillator as a reference for both channels, but with a phase lock time constant in the order of, let's say, 50 seconds, maybe 100, I don't know exactly, because you can see here 0.01 second, I have to shift the scale vertically. This suggests that the phase noise goes like this for the rubidium oscillator, while the crystal oscillator starts to go up here at 0.01 Hertz. So phase locking that channel 1 oscillator to the rubidium oscillator with a time constant corresponding to 0.02 Hertz here would be optimum. And then I would lock, of course, channel 2 to the same reference oscillator. Means I have uncorrelated low noise oscillators down here somewhere from channel 1 and channel 2, but below 0.02 Hertz both channels would have the rubidium oscillator, so they would be the same, so correlation would not help, but both of them would be the rubidium quality which surely would be better than any crystal oscillator I could build. Here is what it looks like in a linear frequency scale. Down to 0.1 Hz the measurement is reliable, although the yellow curve is not reliable because the statistics is not good enough. These are only 394 averages, and the channel 2 is at minus 20 decibels, while the rubidium is at minus 40 approximately. But I can guess the curve would look something like this, and I can see that the channel 1 goes steeply upwards below 0.15 or maybe 0.2. So a phase locking to the rubidium with a corner frequency of 0.02 Hz. That would be probably an optimum source for this kind of measurements. And then, of course, it would be nice to have the channel 2 oscillator improved before locking it.
Now both channels are phase locked to the Infrasound LPRO 101 Rubidium stabilized oscillator. The time constant here is very long. It's about 2200 seconds. And we can see an oscillatory behavior on channel 1. So the locking is not really good. I have to do something with the loop filter. But this is a very slow oscillation. It will not affect performance at times below 100 seconds about. But we can see this peak is because of these oscillations. I have run also with a shorter time constant, 4 times shorter here. And this time oscillations are not so pronounced. The time scale here is 2 seconds per pixel, while here it was 5 seconds per pixel. You can see at 100 seconds it is now both channels at something like 2, 6, 3, 4, 5, 6, 7 times 10 to minus 12. And here the noise in channel 1 was significantly higher. But I have a recording from what it looked like before I was using this phase locking. And here is that. Here channel 1 is free running and channel 2 is locked to channel 1. And the behavior at very long times is of course less good. Here I have set very slow processing parameters for the phase noise, so I can see down to 0.01 Hz offset, and at that point the phase noise is at about minus 40 dBc per Hz. What I can see here is that there is a straight line here, and then there is a second straight line here, and the corner frequency is about 0.15 Hz. And I can see also that the two channels are very similar. At 0.1 Hz, channel 2 is a little better, and all the way here. At 0.2 Hz, that's here, I see about minus 98, and it's well above the imaginary part, which is at about minus 108.
That's 10 decibels down. This is after 7.5 hours about.
Minus 98 at 0.2 Hertz. That's here. That's about 4 decibels more noise than I had earlier in this video. Something has happened with the oscillator. I will look at that in another video, because now I will stop this one here and make a separate about the PLL problems and why it is unstable.